For the first question, we have to first draw the energy band diagram, and it is provided that the semiconductor is in equilibrium. I have already told you in the lecture that we first draw Fermi energy level, and at equilibrium Fermi energy level is a straight line. Now let the extreme points be A and C and the middle point be B. It is also provided that the doping concentration is highest in the middle. Therefore, energy band diagram will look like this. EFI is not important, but I have still drawn it. In the last set of questions also, there was a question which was based on energy band diagram. And you know that free electron concentration is equal to effective density of states in conduction band multiplied by exponential negative of EC minus EF divided by KT. So you can see that when the doping concentration is high, EC minus EF will be smaller. One more point that you have to remember, that even though it is at equilibrium, it does not mean that there is no current flowing inside the semiconductor. The two currents, which are diffusion current and drift current, will cancel each other, providing the net current to be zero, but still the current will be there. Now, for the first option, for X between B and C, the electron diffusion current is directed from C to B. You can see that in the region from B to C, electrons will flow from B to C, but the direction for current is opposite to the direction of flow of electrons. Therefore, the direction for diffusion current density will be in this direction. So, the first option is correct. For X between B and A, the electron drift current is directed from B to A. Drift current requires the direction of electric field. So, we will be needing the help of energy band diagram. Assume that you are here, and I have told you already that the direction of the electric field will be in the direction as if we have to climb the mountain with EC to be the slope of the mountain. Here you have to assume the slope is circular. So this direction will be of electric field. Therefore, the electron drift current will be in the same direction. Remember that drift current is in the direction of electric field, irrespective of whether the drift current is caused due to electrons or holes. So, the B option is also correct. Third option says, for X between V and C, the electric field is directed from B to C. We are still standing at the same point, and from B to C, the electric field will be in this direction for the same reason I just described. So, C option is also correct. For X between B and A, the electric field is directed from A to B. We already found the direction of electric field, which was from B to A. Therefore, this option is false. For the second question, we have intrinsic carrier concentration 1.45 into 10 raised to the power 10 per centimeter cube. Donor concentration is provided to be equal to 5 into 10 raised to the power 14 per centimeter cube. You know that the formula for free electron concentration is and you also know generally when the doping concentration is significantly greater than intrinsic carrier concentration, we usually ignore this term, and after ignoring we get free electron concentration to be equal to ND. Here, if we would have ignored the intrinsic carrier concentration, then we would get free electron concentration to be equal to 5 into 10 raised to the power 14 per centimeter cube. But the exact value will be slightly greater than this value. After considering the value of Ni square, the free electron concentration will increase, even though a little, but still it will increase. For whole concentration, we have Ni square divided by free electron concentration. If we ignore the intrinsic carrier concentration, then the whole concentration will come out 4.2 into 10 raised to the power 5 per centimeter cube. But if we include the intrinsic carrier concentration, whole concentration will slightly decrease. Therefore, considering the exact values, the right option will be C option. For third question, we have length 0.1 centimeter, which we can write as 10 raised to the power minus 3 meter. Area is provided 100 micrometer square, which can be written as 10 raised to the power minus 10 meter square. Majority carrier concentration, which is electron concentration, is equal to 5 into 10 raised to the power 20 per meter cube. Mobility of free electron is provided 0.13 meter square per volt second, and the value of charge Q is provided 1.6 into 10 raised to the power minus 19 coulomb. We know that conductivity is equal to charge carrier concentration multiplied by magnitude of charge multiplied by mobility of charge carriers. Also, we know that resistivity is equal to 1 upon conductivity and resistance is equal to resistivity multiplied by length of the semiconductor divided by cross-sectional area of the semiconductor. We can also write resistance to be equal to now we simply have to put the value of different parameters. After calculating, we will find the value 10 raised to the power 6. In questions like this, the important thing to remember is to convert all the parameters in SI unit. For the fourth question, you know that electron diffusion current density is equal to Q multiplied by diffusion constant of electron multiplied by concentration gradient. Therefore, electron diffusion current will be equal to diffusion current density multiplied by area. Now we have to simply put the value of different parameters, and also since we have to simply find the magnitude, therefore we are not concerned about the sign. The value of Q will be equal to 1.6 into 10 raised to the power minus 19. Electron diffusion constant is provided 25 centimeter square per second. Area is provided 0.45 centimeter square, and we can find the concentration gradient by this particular expression. Now we have to simply calculate this expression. After calculating this expression, we will find the value of current to be equal to 162 milliampere, which can also be written as 0.162 ampere. For the fifth question, doping concentration Nd is provided 10 raised to the power 17 per centimeter cube, and intrinsic carrier concentration is provided 1.4 into 10 raised to the power 10 per centimeter cube. You can see that doping concentration is significantly greater than intrinsic carrier concentration. Therefore, majority carrier concentration which is free electron concentration, will be approximately equal to doping concentration. And from mass action law, we have hole concentration equal to square of intrinsic carrier concentration divided by free electron concentration. After calculating, we will find the value of hole concentration approximately equal to 1.96 into 10 raised to the power 3 per centimeter cube.